In the decades to come, as scientists pieced together what was really going on, it became clear that X-rays have nothing to do with the supernatural. They are merely another part of the electromagnetic spectrum. At the top of that spectrum, vibrating quite fast, is blue and violet light, and beyond it the light we can't see, ultraviolet. And now a form of radiation emerges that is very high frequency indeed, vibrating extremely fast, X-radiation. But the visible glow in the vacuum tube would lead scientists somewhere very different. It wouldn't help them communicate with the dead, but in its own way it would be just as revolutionary. One of the centres of research into the strange characteristics of vacuum tubes was Cambridge. Here, Maxwell's research lab was now run by a physicist called J.J. Thomson. It's one of Thomson's misfortunes to have gone down in history for an incident that's almost absurd in its triviality. In the 1920s, he's reputed to have shouted at a couple of undergraduates training for the 1924 Olympics in the Great Court at Trinity College. One of them went on to win gold. But Thomson, like Maxwell, was a brilliant scientist, and in the closing decades of the 19th century, he designed his own cathode ray tube to investigate this very peculiar form of light. This is a replica of what Thomson designed, and what's special about it is that it allows the cathode rays to be affected simultaneously by electric and magnetic forces. And the experiment that J.J. Thomson did with this tube would have the most dramatic consequences. Thomson was not a practical man. In fact, he was notoriously clumsy. Yet using his new tube, he performed a series of hugely important experiments. He would turn the cathode ray tube on. You'd see a glow and a bright point at the other end of the tube. Turn the electromagnets on, the position of the dot moves. The magnets are deflecting the cathode rays. Thomson repeated the experiment time and time again and measured the size of the deflection. Whatever was coming down the tube was clearly not a wave. It only made sense if it was a stream of particles. Thomson then plugged the figures into Maxwell's famous equations. And the result he got was absolutely dramatic. He found that the particles making up cathode rays are tiny, much, much smaller than atoms, and that was an earth-shattering result. Nobody had ever produced any evidence that there was anything smaller than an atom before. Indeed, some scientists didn't even believe in atoms. Years later, Thomson was to describe his findings in a lecture to the prestigious Institute of Electrical Engineers.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, will be too small to have been detected by any means then known to science.
Today, we know these tiny particles as electrons.
This was really revolutionary stuff. And what was so exciting about it was that the technology to begin to pull atoms apart, to begin to tell a story about the most fundamental building blocks of the world, came straight from light technology. Vacuum pumps, light bulbs, vacuum tubes. It was by thinking about those bits of machinery that the atom began to be torn apart.
Yet it's one of history's great ironies that at the time nobody realized science was on the verge of a breakthrough that would turn physics and the world on their heads.
By the end of the 19th century, most scientists in Europe and overseas reckoned that in many ways the task of physics was over. The basic problems had been solved. We knew how light, electricity and magnetism worked. We understood the problems of heat and engineering. Physics turned into a search not for great new theories, but just for better measurements.
One of these measurements concerned the production of light bulbs, by now a hugely important and influential commercial activity.